So the first test that we're doing is the chi-square test for independence to check for a cause and effect kind of relationship between our two variables. The second is going to be looking for a linear correlative relationship, and that's kind of what we'll be talking about in chapter 14 is how to check for that or how to test for that. So we're going to start with talking about scatter plots or scatter diagrams. So the whole idea for chapter 14 is this concept of correlation. So if you have bivariate data, meaning you have two variables, you can check for the correlation, i.e. the relationship between those two variables. So if these two variables are related, like what kind of relationship do they have? Like mathematical relationship. So when we say correlation, we don't just mean any old relationship. What we're really talking about is like a linear relationship, and we'll talk about the strength or weakness relative of that linear relationship. So you can calculate a correlation for any two variables, and you'll get a number that comes out, and that number will tell you, oh, these are strongly, weakly, moderately correlated, all that kind of thing, okay? And really when we talk about correlation, we're talking about a linear relationship, so like a straight line. So to do this kind of thing, if it's a linear relationship, we have to identify the independent and dependent variable. So like which variable is the cause and which is the effect, essentially. So again, independent is the cause and the dependent is the effect. Okay, so just as a little concept check, we have the size of someone's hand related to their height. So the two variables are their height and their size of their hand, excuse me. Which one do you think is the independent variable? Which is the cause? The height, right? You expect if you're a taller person that kind of overall, like all your body parts are proportionally, larger as well, right? You have longer leg, you have longer arm, you have bigger feet, all that kind of stuff. If a company spends more on advertising, will the company sell more of its product? So the two variables there are advertising spend and then like profit, product sold. Revenue maybe is the word for that. I'm not an econ person. Which one is the independent variable? Which is the cause? The advertising budget is your cause. You're hoping that the effect is then you sell more stuff, right? That selling more stuff doesn't make you spend more on advertising. Maybe it does in a way, right? You have to be a pretty rich company to afford advertising. I don't know. I think that the advertising budget is your independent, though. Everybody feel okay doing this? You're kind of just using some common sense to piece out, okay, like which one feels like the cause and which one is the effect. One way that we can visually examine the relationship between our two variables is with something called a scatter plot. So all we do is we treat each individual that we sample as one point where their response to the independent variable is our x coordinate and their response to the dependent variable is the y coordinate. So to make a scatter plot, we need to decide which variable goes on each axis. Remember, x is the independent variable. That's your cause variable, and the y is your effect. Then you should label and scale your axes. So, if the x-axis is, advertising budget and the y-axis is revenue, you should also say like in dollars or something, probably American dollars. And then pick a scale. So like, maybe it's by hundreds of thousands of dollars or something for revenues and tens of thousands of dollars for advertising budget or something. And then plot your individual data values. So when we look at a scatter plot, we're going to be looking at kind of four potential things. So I'm going to be looking first at the direction. And then the form, and the strength of the relationship, and then as well any potential outlier. So when I say direction, basically what I'm talking about is slope, right? So is the data tend to increase as we go from left to right, or does it tend to decrease as we go from left to right? So we say that the direction is positive if the slope is positive, we're increasing as we move from left to right, and the direction is negative if we're decreasing as we move from left to right. When we talk about form, that's essentially the shape of the graph. So does the data look like a line? Does it look like a parabola, like a hyperbola, something else, a sine wave or something, right? So we're going back and thinking about what are the different function types? What do their graphs look like from our Algebra 2 or pre-calculus courses? The strength is going to be describing how tightly does that data fit onto a line, or whatever the curve is that we think the shape is. Is everybody okay with that? And then we know what outliers are. We've talked about those, right? Okay. So when we talk about direction, we want to talk about whether we have a positive or a negative association. So if I look at this guy, what does the direction appear to be here? We'd say it has a negative association because as we move from left to right, the graph is kind of tending, or the data's trending down. So we'd say that the direction here is negative or has a negative association. What is the shape here, or the form? That's the word we used. I mean, it kind of looks linear, right, in a way, but it also, to me, looks curved. So it could be I would say that this looks like exponential to me, kind of looks like a hyperbola. You guys buy that? But it still has some linear relationship here. When we talk about the strength, this thing is not super tight, it's just like a thin little line of points that look like a hyperbola. Yes, sir.
Yes, if you have not a super defined line, you see that dot kind of next to 500 right there.
Yeah.
Would that be considered an outlier?
Yeah, we're going to get there. Probably. I think we have two potential outlier candidates. I'd say this guy and then this guy. Both look like potential outliers. So the strength here, since it's not like a super tight line, but you can definitely still see a shape to it, right? I'd say this is probably moderate, moderately strong. But it's not super well defined. It's still if I draw drew this, it'd be like using a really thick marker as opposed to like a really fine pencil. It's kind of the way I think about it. And then we said that it looks like there's potentially two outliers, one here at like, 87 and 450 or 460, and then one here at 20, 500 or whatever.
We're gonna find the outliers just by like eyeballing it.
Right now, all we're talking about is visual inspection. We can do more to check those things, but right now, we're just talking about using our eyes. Okay, so we said moderately strong, negative, curved relationship, and two distinct clusters. So again, if I look at this graph, there's like a bunch of here and a bunch down here, but not a lot here in the middle. That's what I mean by the two distinct clusters. And it looks like there's two possible outliers that we talked about here. So again, the strength, direction, and form. Those are the three things that we're looking for in our description. So the strength is describing how tightly grouped the things is together. The direction is positive or negative, whether it's the data is increasing or decreasing. And the form is the shape that we're seeing. Feels okay so far? No big deal. Just using some vocab in our eyeballs right now. Okay. So let's describe this scatter plot here. What would we say the direction is? Positive, because it's increasing as we move from left to right, the data. What is the form? I would say linear. I think I agree with that. Appears to just be like pretty straight line. I don't see much curve going on there. The strength. Is this a thick line or a thin line? I would say it's probably pretty thick. Like if I were to draw this so that like all the data is covered with a marker, I need a pretty thick marker to cover it, right? As opposed to just like a little thin guy if everything was like all lined up nice and neat. So I'd say this is moderate. Do we see any outliers? Yeah. This guy maybe, but even he's not really that far away from like the general trend. If I try to like draw a line so all the points are like equally close to each other, even this guy's not that far away from that line. So I'd suspect there's probably not any outliers. That's always okay to say. So positive association is what we said. Again, as we're looking at, looks like a football team or something where we're investigating the relationship between points scored per game and wins. So we said the form is linear. The relationship is fairly strong. I said moderate. That's really the same thing, and it appeared no outliers. Everybody's okay? Okay. So the next thing we're going to talk about is the line of best fit. So the idea is that we want to take our scatter plot and draw in a line that best represents the data. So it doesn't mean that that line is going to necessarily pass through any of the data points, but we want it to be as close as possible to all the data points. So overall, as close as possible. There's lots of different ways to do that. The way that we're going to construct our line of best fit is using something called a mean point. So the mean point is just the point where you have the mean of the x's and the mean of the y's. So when we draw our line of best fit, we want to make sure that passes through the mean point. Now, what I want to emphasize here is the difference between the terms correlation and causation. These two words are very different, especially statistically speaking. Causation, really difficult to prove. That is a difficult thing to prove. Correlation, much easier to prove, but says much less about what's going on. So for example, I have this stapler. It sits on my desk every day, right? I propose to you this stapler repels bears. Because every day I've come in here, I've never seen a bear in this classroom as long as this stapler's been in there. That's causation, right? The stapler's causing the bears to go away. Am I full of crap? Yeah, probably. It's very unlikely that this stapler has anything to, or this tape has anything to do with repelling bears. What is actually causing there to be no bears here? There's no bears that live in Oakland County, right? Like, other than at the Detroit Zoo. But that's the real cause, right? What do I have here, though, between my tape dispenser and bears is correlation. There is a relationship between these two things. Is the stapler causing or the tape dispenser causing the relationship? God, I would think not. Seems super unlikely that it's the cause, but there is a relationship here, and it's a very strong relationship. But if it makes no sense logically, like, what does the correlation really tell us? That's my idea. So in our example of the tape dispenser and the bears, there's a confounding variable that's really causing the relationship that we're seeing. That confounding variable is where we're at, the location, right? If we're outside in, like, Alaska, I don't think that tape dispenser is going to do me a whole lot of good. What do you guys feel good? Okay, wanted to kind of talk through that. So here's another example. If 100% of NDP, or 100% of students at NDP get accepted to colleges, we could easily say that attending NDP causes a student to get accepted to at least one college. Are we talking about correlation or causation here? This, I think, is a correlative relationship. I don't think that your attendance at NDP for most of us is the thing that's causing you to get into college. How many of you, if you went to a public school, would still be planning on attending college? Probably everybody in the room, right? That didn't change because you went to NDP. You know, the colleges you may be applying to may have changed, but the act of wanting to attend college probably didn't. You know what I'm saying? There's another example of something that, like, we said cause in here, but think about it rationally, and I don't think that the school is the cause, at least this kind of a school. You know what I mean? So that's section 1. That's a pretty exciting section. Section 2, we're going to actually start measuring correlation numerically. So again, we can look at a scatter plot. We can use our eyes to just kind of talk about the strength, direction, form of the relationship between the two quantitative variables. But we're not doing anything like objective there. Like, all of what we're doing is pretty subjective, right? It's kind of like, well, that's what it looks like to me. Can you prove that? Well, no, I'm just using my eyeballs to look at it. So there are numeric measurements for correlation, and that's what we're going to be talking about, how to compute here today. So the first one is the Pearson Product Moment Correlation Coefficient. That's what PMCC stands for. Pearson Product Moment Correlation Coefficient. We abbreviate that with the letter R, the lowercase letter R. Maybe we remember this from pre-calculus or algebra 2. I think we talk about R in both those courses. This statistic R gives us a measurement of the direction and strength for linear relationships. So facts about this statistic R: it's always a number between -1 and +1. Positive values of R imply a positive association. Negative values and negative associations. The closer we get to 0, the linear relationship weakens. So your weakest possible linear relationship is at 0. And the strength of the linear relationship increases as we move away from 0. So your most linear relationships are at -1 or at +1. In the case of these values of -1 and +1, these only occur if the data that you're building that's in your scatter plot would actually be points on a line. So it's not just like they kind of look like a line, but no, I can actually make a line, and that line passes through every single one of the points in my data set. Everybody cool? This sound familiar, right? We talked about this before, I think, right? Did we do this in pre-calculus? I don't even remember. Luca doesn't remember either. Let's say that we did, since you guys don't remember either. You won't argue with me if you're like, I don't remember doing that, but he seems pretty confident. I guess we did. So let's set up some guidelines here to help us interpret our R values. So if we have R between, or the magnitude of R, so plus or minus, between 0 and 0.25, we'll call that very weak. Between 0.25 and 5, weak. Between 0.5 and 0.75, moderately strong. And then 0.75 to 1, very strong. So this is just like a way to help classify what we're seeing with our eyes. And the thing that's tough is, seeing something like 0.49 versus 0.6 or something. Like seeing the difference of that with your eyes is good luck with that. The stuff very close to 1 or very close to 0 is obvious. The stuff in the middle here is tough. All right. So what I want to do here is just give you a little bit of a visual of some scatter plots and their respective R values to give you a visual to go with the number. So this is a R of approximately 0. Notice no pattern that we can see. If I look at the next one, the R value is -0.3. Not much difference between those two visually, right? If you really look hard at this one, I guess it's kind of trending down as I move from left to right, but probably most of us would say this is no relationship. Here, this is positive 0.5. Again, we can see there's a little bit of upward, but to me, I don't see much difference between this one and this one, other than one tends to be going down, the other tends to be going up. But the correlations are quite different. This is -0.7. I think that here we're starting to see, okay, that looks, like a big fat line. And I compared that to this one at positive 0.9. That doesn't look much thinner than this one does it? But it is a much better correlation. This one, though, I think that everyone would look at this and be like, okay, that's strong association or strong negative association there. So it can be quite challenging with just our eyes on determining like what the relationship is, what the correlative relationship is, right? So the computation here is really helpful because it eliminates like the subjectivity of it. All right. Where did my thing go? Okay. Ooh. For each graph, estimate the correlation R and state the plot's direction, form, and strength. Who wants to take a stab at this one? Let's start with estimating an R. There's nothing to compute here. You're just kind of using the intuition that we built up in the previous one. 0.75 seems pretty reasonable. The actual number I had written down was 0.8, so that's a pretty good guess. The direction here is positive. The form is linear, and the strength is strong. Everybody agree? Okay. Let's look at the next one. Point 1. Yeah, what I have written down here is 0.3. So like you're in the ballpark. The point of the matter, though, is you'd say this is direction, positive, strength, weak, and the form. I mean, you say linear, right? But yeah, good. Oops. What about this guy?
You can kind of see it going up.
You think so? Because like these points are lower than these points.
Yeah, that's true.
But then these points are lower than those points. This to me looks like R equals 0. Like this looks like there's no linear relationship at all. This looks just like a random mess of stuff. Because if I go from like left to right, like these guys are all not really going anywhere, but these ones are higher than those ones, but these ones are lower than those ones. So like anywhere I go, there doesn't seem like there's a trend of like the data going up or down. It just seems like there's as much stuff up here that's higher than stuff down there, but then there's the same amount of stuff down there that's like lower than the stuff over there. I mean, it's just like, it's a big mess to me.
If it's R equals 0, then we can't do anything else.
Yeah, there's no relationship. That's what it's saying, is the data is ostensibly random. Oops. How about this guy?
At what point?
Well, negative or positive? I think it looks negative to me. But I think it's going to be negative and it's going to be weak. I had negative 0.3 was what was written down on my sheet for what this was.
What's in a 0.1?
I mean, it's not going to look much different than this. So like if you can find any detectable like up or down pattern, it's probably going to be closer to 0.3 than 0.1. But all we're talking about right now is kind of building some intuition. So like, I would not ask you, like, we'll grade you massively, where if you're in the right ballpark, you're good. So if you had something that looked like this and you said it was like negative 0.5, well, I'm marking that down because clearly it's positive and it's much closer to 1 than 0, right? But if you called this 0.8 and someone else said 0.9 and someone else said 0.75, those are all strongs. I would count them all the same. You know what I mean? Or like this guy is weak, as long as you had a positive value, 0.1, 0.2, 0.3, whatever, it's all fine. You know what I'm saying? Like it's not that the estimate is not that big of a deal. Okay. So some more facts about R. So if you screwed up which variable was your independent or dependent variable, it's going to have no effect on R. It doesn't change with the unit of measurement. So if I converted, if I did my study in feet for X and pounds for Y, and then I changed X to kilometers or something instead of feet, the R value is going to remain the same. The units will not affect it, as long as I do the unit conversion to the data. The number R has no unit attached to it. It's just a number. It's a statistic. So it's not a percentage. It's not feet. It's not inches. It's not pounds. It's just a number. And just as a reminder, to do this, we can only do this if our variables are quantitative, meaning they're numeric. The R value doesn't describe any curved relationships, no matter how strong that curved relationship may be. We'll talk about another relation or another measurement later on where we're able to do that. And we say correlation is not resistant, i.e. that value for R can be strongly affected by just a few outlier observations. Everybody's okay? And then the last one is that this is just not even, it's not a complete summary. It's not like the end-all be-all. It's just one statistic. Yeah.
So for the second one, it's not a close relationship, meaning it only works if it's linear.
The value for R will only describe the linear relationship in the data. Even if the data looks like an awesome exponential function, like a great looking hyperbola, the R value is going to not be great because that's not very linear. R is only describing the linearness of your relationship. There are other statistics that can detect like a curved relationship, and I think we look at that a little later. All right, so let's talk about how we do the calculation. Here's the formula. So it's going to be 1 over n times the sum of the first x value minus the mean for the x's divided by the standard deviation of the x's times the first y value minus the mean for y's divided by standard deviation of y's plus, I'll do that for the same thing for the second values and the third values and the fourth values for the entire data set. We'll add up all those products, and that's going to be our R. So it's basically like a scaled average distance is kind of what this boils down to. All right. So let's look at this data set we have here. This looks like it's has to do with miles driven and then the value of a vehicle. So if I look at this, here's my line of best fit. I computed this using a calculator. It says the formula here is y equals, the y is price, and then the y-intercept is like 38,000 and change, minus 0.16, that's like the slope of this line, times miles driven. We're told that the heck is S? Not sure. And the R squared is different than R. We'll talk about what R squared is later. But notice here that when I flip the axes, I got a different best fit line, right? But that r squared value, which is related to r, still the same. So if we take a look at these 4 scatter plots here, you want to hear something crazy? All 4 of these scatter plots have the exact same R value. The point of what, or the takeaway is that, remember, R is just describing the linear relationship, the strength of the linear relationship, and it's strongly affected by outliers. So if I look at this, like, that's reasonably line-like. Clearly there's a better relationship for this though, right? You can see this is distinctly parabolic. You guys agree? This definitely looks linear, but it's kind of messy, right? That's why the R value is not very close to 1. Here, it looks like a perfect line, except for this one stupid outlier, which is dragging down your R value, which would be probably 0.99 if you threw this guy out. And over here, I have there's no linear relationship here. It's like straight vertical. But if I throw one big enough outlier in it, it looks like, oh, there's a linear relationship kind of going right in through there. So again, the R value is not like your end-all be-all for linear relationship. You can fool your R value with outliers really easily. And things that are clearly not linear can still give you pretty good R values. Does that feel okay? So it's not the end-all be-all statistic for the relationship between these 2 variables. It's just, when stuff looks like this, it's pretty good. But if you have some kooky, crazy stuff, maybe not that great of a measurement. And then, in fact, each of these all have the same best fit line as well, which is cuckoo crazy to think about.
So it's not that we can't find an R value for a curve.
Yeah, it's just maybe not the best representation, right? Like, oh, this data is pretty linear. Sure.
Until you get to
But if it's actually really parabolic, if I try to predict a value out here, if it's parabolic, I'm going to get a vastly different answer than if I use a prediction that's linear, which is going to give you a value up here. So you want to try to make sure that, in practice, if you're doing this as a working statistician or mathematician, you'd want to make sure, is the relationship that I'm using to model this situation even make sense for this situation? And oftentimes linear relationships, not really a very good choice. And sometimes they are. So again, to illustrate the impact of outliers, it looks like we have, this is a Gessel score, which I think is like some kind of child intelligence test. And then the age at which they said their first word. So if I look at this, it looks like there's 2 obvious outliers, right? This kid here, child 19, and this kid over here, child 18. What I want to talk about here is what this looks like what the R and line of best fit look like if I include everybody, and if I throw out one outlier, the other, or both. Everybody's okay? So with all of the children, our R value is negative 0.64. If I throw out child 19, our R value jumps up to negative 0.76. If I throw out child 18, it drops to negative 0.33. So you see that removal of some outliers can improve your R value. By removing 19, we got a better R value. And removal of some outliers may hurt your R value. Removal of child 18 made the R value worse. Everybody's okay with this idea? That again, the removal of outliers is not necessarily going to improve your R value. It could hurt your R value. But the point of it is this this outlier is probably not representative. Probably shouldn't be there. Even if it's making your R value better. You know what I'm saying? So one way to build our line of best fit is using a least squares line. So the idea with a least squares line is basically we draw on a line of best fit and we look at the vertical distance from our point to that line of best fit. And then we use that vertical distance to kind of make a square. And we do that for every data point. And we compute the area of each of those squares and we add up all the areas. And the idea with the least squares line is that we move that line around until we've minimized the sum of all those areas. So that essentially our line is as close as possible to all of the data set. Everybody's okay with that? Now, if I have an outlier that's really far away from my line, my potential line of best fit, that's making an enormous square, like a square with area as big as all the rest of the squares combined, that's going to have a huge impact, right? So especially if the outlier is in only one direction. So if I have something that's extremely far left and right, that's going to have a lot of pull on our R value. We call those guys influential. So we say an outlier is an observation that lies outside the overall pattern of the other observations. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. So if I go back and I look here, this child, 19, is an outlier in the y direction, right? It's much higher than the rest of our points. But there's lots of x's, lots of points that have a similar x value, right? Child 18 is an outlier in the x direction because there's no points that are near 40 in the x. That's what we're talking about. And we noticed that removal of child 18 had a much bigger impact on our R value than the removal of child 19. Is everybody okay with that idea? So those outliers in the x direction are really the ones that you want to watch about. The second type of R value is called Pearson's rank correlation coefficient. So this is another value or another way to describe the relationship between the two variables. So the Spearman's rank correlation coefficient is only going to measure if there's a consistent relationship. So it's not strictly linear. So all it's going to look for is if there's a strict increasing, decreasing relationship between the two variables. So this statistic would ignore form, right? Like the Pearson product moment correlation coefficient is very form dependent, right? The shape of your curve matters a lot there. Here, the shape does not matter. So the symbol we use to describe the Spearman's rank correlation coefficient is R sub s, or sometimes you use the Greek letter rho. I think I use R sub s almost always. So again, R sub s is a number between -1 and 1. Positive RS's indicate a positive direction in the relationship. Negatives indicate a negative. Values near 0 indicate a very weak relationship. The strength of our relationship increases as we move away from 0. And those extreme values, -1 and +1, occur only when we have a perfect rank order relationship. So let's look at an example. So here we have some cell phone data. It says mobile phones often lose their resale value quickly after they are purchased. The following data is collected for one particular model. So it's the month since purchase is our X, and then we have the percent change in value as our Y, since the value is dependent on the months. Everybody's okay, or how old the phone is. So here's our graph. If I look at the graph here, this looks like a nice exponential curve, right? Maybe a little bit linear in here, but overall it looks exponential to me as opposed to linear. Do you guys agree? So if I did the Pearson value for R on that, I get -0.874. If I want to do the Spearman, what I need to do is first change our data into rank order data. So what we do is we number the data for each column in order from highest to lowest. So this would be 1, 2, 3, 4, 5, 6, 7, yada, yada, yada. And then here would be 1, 2, 3, 4, 5, yada, yada, yada. Right? Because 0 is the biggest value. Everybody's okay? So 24 becomes 1, and 0 becomes 13. And we do the same in the other column. So 0 becomes 1, and then -87 would become 13. So what we have then is this data set. So far, so good. What we do now is just do the okay, so we'd graph the scatter plot. Look at that. Pretty stinking linear, isn't it? Now, to calculate the Spearman, all we do is the Pearson calculation on this data set. So what this is telling me here is -0.995 for my Spearman coefficient, is I have a very strong negative relationship between this data. Doesn't tell me linear or what shape that relationship it is, but it definitely is showing that, yeah, this thing is, the older your phone is, the less valuable it's becoming. Dead to rights, that's pretty certain. Blah, 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 blah. If we reverse the rankings, what happens if I had ordered this in the wrong way? So I put the lowest value at 1 and the highest value at 13 instead. So our data set would have looked like this instead, right? So my new rank order graph looks like this. What do you notice? It's the exact same. All right. What if we have ties in our data set? How do I do the numbering? So we have some hours here. Notice in the hours, though, I have 2 people at 3.5, and then 3 people at 6.5. And if I look at the Y's, do I have any repeats there? Didn't look like it. So again, we want to rank them. We're going to put them in order from greatest to least. So the least value here was, I'm sorry, the greatest value in the x's was 7, so I got a 1. The next greatest value is 6.5. So all the 6.5s get 2, right? Because they're the next highest value. But then the next highest value is actually 1, 2, 3, 4. It's actually going to be the 5th highest value. So 6 is next, 7, 6.5, 6. But 6 is the 5th number, so that jumps all the way to 5, et cetera, as we number down. Everybody's okay with this? If you've been at like this is the same scoring used at like a track and field meet. If you have a tie in the high jump or something, you know, 2 kids tie for first place, the next place is 3rd. There is no second place awarded. I don't know if there's any. So this is just what we've talked through. So we've got their ranks. Okay. So this is our ordering, right? But for these 3 values, we're not actually going to use the number 2. Because these 3 values are occupying places 2, 3, and 4. We have to average those 3 numbers, and we should be using 3. The same thing is true out here for the last 2 values. Those are occupying places 10 and 11. So the rank number we have to use is actually the average of 10 and 11. So this is actually what we're going to put in the calculator now. So just because these guys were second place, tied, doesn't mean that's going to be the rank number. That's their order. To get their rank, I have to average the places that those are occupying. So places 2nd, 3rd, and 4th. So I take the average of those 3 places, and that's their rank. Again, if you're at a track and field meet and you have 2 people tied for first in the high jump, they both don't get first place points. They get the average of the first and second place points. All right. So when I do that, I take this data and then I just do the Pearson calculation on it, and that'll give me my R value for Spearman, or my Spearman statistic. Notice that if you did this without re-ranking them, if you just did the places and not the ranks, you get a totally different number. So it is really important when we're doing this to make sure we're doing the rankings correctly. All right, so let's summarize here. We have 2 statistics we talked about today, the Pearson product moment correlation coefficient and the Spearman's statistic. So in outliers, we have a graph like this. That's a huge outlier, right? Both in the x direction and in the y direction. So overall, this data has a negative trend, but this one stupid outlier is dragging the Pearson product, or the Pearson statistic way up into being positive. That seems ridiculous, right? It's saying that, oh, that's the relationship right there. If I do the same thing with a Spearman, though, look at the effect. My R value for Spearman is negative 0.48. We've still retained the negative relationship even though this outlier is there. So the takeaway here is that the Pearson statistic is much more impacted by the presence of an outlier than the Spearman is. The Spearman is more resistant to outliers than the Pearson. So another thing to keep in mind here, so in mathematics we have this term called monotonic, and we say a function is monotonic if it is like either all the time it's increasing or staying the same, and we say it's monotonically increasing, or you can say it's monotonically decreasing if the whole time it's getting smaller or staying the same. So examples of monotonically increasing functions and monotonically decreasing functions. Yes.
What does it mean by only decreasing or decreasing?
So if I look at this function, it's only getting bigger or staying the same, right? Same thing with this one, only getting bigger or staying the same, only getting bigger or staying the same. This one is only getting smaller or staying the same, only getting smaller, staying the same, only getting smaller, staying the same.
So it's not going to go like up.
Right. So like a sine graph is not monatomic because it's going up and then coming down, where a parabola is going down and then coming up, not monatomic. So the Spearman correlate, or the Spearman statistic, is really just a measure of how monotonic it is, like how consistently increasing or decreasing all the time it is. So graphs that have bad or are not monatomic will do very poorly with a Spearman statistic. So things like a sine wave or a parabola or an absolute value, all of those are going to be bad, give you bad Spearman statistics, even in the case where they might be able to be well represented using a Pearson. And we're at the end here for today. Let's go and look a little bit at the in-class examples. We'll take a look at some of those today. All right, for the following situations, identify which is the independent, which is the dependent variable. Comment on whether you believe the variables will be strongly, weakly, or weakly correlated and why. Part A, the ACT score of a student and the amount of sleep per night the student gets on average. Which one is the independent and dependent variable here?
The amount of sleep.
Good. The amount of sleep is the independent. Now, do you think there's going to be, what level of correlation do you think there's going to be between these? Now, just say like weak, moderate, or strong.
Oh, weak.
Why do you say that?
Just for like knowing about the ACT, like some people are just better at it. Like
There's things that matter way more than how much sleep you're getting on average, right? Will sleep have some effect? Yeah, maybe. But like how smart you are matters a whole heap more than how much sleep you're getting. You know? All right. B, the number of hours spent exercising per week and the number of years a person lives.
the number of exercising is independent.
Good.
And then that's moderate correlation.
Yeah, I would say this is probably moderate to strong, right? Like there are things that like even exercising can't protect you against, like accidents, or violence. Well, maybe if you're like a professional fighter, it helps you against violence, but it's not going to help you against a gun. But in general, like, it seems like if you are getting a lot of exercise, you typically have better long-term health outcomes. The things that kill you in old age tend to, not get you as quick. All right, the distance you live from a body of water and the amount of snow you receive in your backyard every year.
The distance you live from a body of water.
Good. And the level of correlation here?
Well,
This is the Michigan bias.
yeah.
This is
It
weak.
kind of depends on the location.
Yeah, think about Hawaii.
No.
You live on the beach in Hawaii. You going to see any snow in your backyard? No. You're only thinking of this because of lake effect snow in Michigan. I tried to
Yeah.
trick you here.
That's exactly what I meant.
Yeah. So again, like, what is it? It's latitude probably has a much bigger impact on the amount of snow you're receiving than anything else. And relative elevation, I guess. Because even if you're at like a mountain at a relatively temperate latitude, you still get snow. All right. Next one. So we're just going to give the direction, form, and strength for each of the following scatter plots. On A, direction, form, linear, I agree. Strength, yep, sounds good to me. B, yeah, seems like there's no correlation here at all, right? So you can't really say anything about any of them. How about C? Positive,
Linear.
positive, linear, and strong. I agree. All right. For the following set of data, plot the scatter diagram, then draw a sketch for the line of best fit. Make sure to include the mean point. So let me just show you this on the calculator, because I hate doing things by hand. So I'm going to go stat, edit, and I'm going to type in my x's into a list and my y's into a list. So 73, 68, 67, 75, 67, 68, 72, 68, 72. And then type in the other one. So 11, 10, 9, 13, 8, 8, 12, 9, 10. Okay. And just clear this list out too, because I'm going to do something in here in a second. All right. So there's going to be the points that I'm going to plot. Before I do that, though, I also want to graph that mean point. So I'm going to do exit out of here. I'll do stat, calc, two variable statistics using L1 and L2. Hit calculate. Uh-oh. Apparently I missed a point in one of these. That's always great. Oh dear. All right, let's see. 11, 10, 9, 8, 13, 8, 8, 12, 9, 10. Uh-oh, I did too many on this side. 73, 68, 67, 75, 67, 68, 72, 68, 72. Now, where Ah, there it is. I missed the 9. Okay. There we go. All right. So there's my x mean. If I scroll down, there's my y mean. So I'll go back, stat, edit. And up here I'm going to go to the title for L3. I'll do vars, statistics, and I'll pick x mean. Or I could have just typed the number in. Ooh, it really wouldn't let me do that. Why not? Okay. So I'll just type it here then. Enter. Vars, statistics, x mean, enter. Okay. And then we'll do vars, statistics, y mean, enter. Okay. So if I go to stat plot, I'm going to turn plot 1 on, and I'm going to graph a scatter plot, L1 and L2, and I'll use the squares. Then I'll go to plot 2. I'm going to turn that one on. I'm going to graph a scatter plot. This time I'm going to graph L3 and L4, which is just 1 point. It's just my mean point. And I'll use the plus sign. And to look at this, I'm going to do zoom statistic or zoom stat. So 9. So there's my scatter plot. This is my mean point. So far, so good. To draw my best fit line now, I'm going to exit out of here. And I'm going to do stat, calc, and I'm going to pick linreg. I'm going to do that on L1 and L2. I'm going to store that equation into Y1. So I'll press vars, yvars, function, Y1. Hit calculate. So this is the equation for my best fit line. If I look at Y1, it's now in there. So if I hit graph, there's my best fit line going right through my mean point. Does that feel okay?
How would we put that on paper?
Well, you would have just like plotted the points and then like guesstimated where the line is. It just needed to go through the mean point. But my guess is that what you would have drawn would have been fairly close to this. When I'm doing this in practice, I'm like, okay, if I got 4 below and 4 above, that seems, and then like 1 almost on there, it's probably what I'm trying to aim for. Is usually a pretty decent estimate. Okay. Feel okay there? Let's do another one. So it says, each member of a statistics class ran a 40-yard sprint and then did a long jump after their sprint. The table below shows the sprint times in seconds and the long jump distances in inches. Make a scatter plot. Explain what you chose as your independent and dependent variables. So I'll start putting the scatter plots in. What is our independent and dependent variable here?
The 40 time is independent.
Yeah, you'd expect that the faster persons can jump the furthest. That tends to be how things work. Dirty little secret about track and field is most of the events are just a measure of who's the fastest. That if you lined up like, oh my gosh, what did I do? If you lined up all the shot putters and had them run 100 meter, the fastest shot putter is probably the guy that throws the furthest also.
Really? You can shot put?
Which is really weird to think about. Yep. Because explosive strength is essentially what you're doing. You're just translating horizontal speed into like the shot put. Yep. Is that most events boils down to the fastest person is typically the best person in the event, particularly at like a high school level. Now that can change, you know, with technique. right? So if you have really highly trained, but at like the introductory level, your fastest people are usually your best ones. Even if it's an event that doesn't seem like the speed part of it is that important, like pole vault or something. Turns out the best pole vaulters are all the fastest pole vaulters. I did it again. Dag nabbit. That's frustrating. All right, so 725, 68, 4, 630. Oh my goodness, it's way back here somewhere. It's the 578. That's a bummer. It's a lot of things to replace. I don't know how to insert one spot in here either. To just like,
You can't just go second and third.
I don't know, I guess I should have tried it. I always remember this being like an incredible hassle when you forget one. All right, so it says make a scatter plot. And then it talks about your R value. Okay, so let's do that. So I'm going to turn these, or I'm just going to change this to be L5 and L6. No, yeah, L5 and L6. And then I'll turn plot 2 off. That just had that mean point in it. And we'll do zoom stat again. So there's my scatter plot. It says describe the direction, strength, and form. Negative. Linear.
Linear.
Moderately strong. Yeah, or strong even. So the R is this. In the context of the data, what does this mean? That there's a strong relationship between sprint time and long jump. Specifically, the less your sprint time, the longer your jump. Based on your scatter plot, what effect is the person who ran 7.25 seconds? So that's like out here, but jumped 110 inches have on your correlation. So that's this guy here. Your slowest individual, but has a relatively high long jump. What is he doing? Well, he's probably hurting. He's probably making your R value worse, right? Yeah, that's what we mean by that. So let's just see real quick. If I dump him out of here, I don't mind doing this because he's already at the bottom. And then, I gotta do that, probably. 1 second. I'll show you what the new R value is.
Do we only need the mean when we're trying to do the line of best fit?
The mean point?
Yeah.
Yeah, if you're drawing it by hand. So removing that last guy bumped our R value to negative 0.868. So we picked up a little bit, not a ton, because the direction in which he's an outlier is really only in the Y, right?
This girl. Literally, no.